Uh, Today's class is continuing the introductory guidance to the quantum mechanics. The topic is about the time independent and the time dependent Schrodinger equation and the wave function. It's lesson number 9. So previously we have started to talk about the Schrodinger equation and how its wave function were introduced to describe the behavior and the motion of the system that we are dealing with, but in terms of quantum mechanics, not classical mechanics. So simply Schrodinger equation would be an analog or similar version of the second law, or which is maybe Newton's law of any classical mechanics, like the summation of forces equal mass, the force is equal the summation of mass multiplied by the acceleration. But in the classical mechanics describing the motion and behavior of the particles or any system, were relying on determining the position x and the momentum of that particles, rather than in quantum mechanics we are dealing with something different description, because we are talking about and going into the atomistic levels. So we need to define the function which is called wave function. So Schrodinger equation itself is a differential equation. Through this Schrodinger equation we are expressing the wave function, which is itself describing the behavior and the nature and the movement of the system, which could be particle, atoms, electrons, anything else that we are dealing with. So how can we describe the particle in classical or quantum mechanics? As we noted before, that in classical, if we can calculate precisely the position for the particle along x direction, suppose that there's an atoms or electron, they are moving in the x direction, and we can determine that particle position and its momentum at specific time. Suppose it could be any time, like time t. So the future position prediction of that particle would be possible. By knowing those two values, the momentum and the position, we can determine the position and momentum of that particle or system at any future position in time precisely, because it's simply dealing the system as only particles, solid bulk material. But in quantum mechanics it's totally different, but in the similar way, in somewhat different translation of the meaning of dealing that system. So due to the nature duality of wave function, because as we mentioned that wave function is describing the nature, the behavior of the system and particle, the Heisenberg principle works there. So Heisenberg probability principle, they are describing the probability of finding the particle or atom, its momentum and its position at some specific instant of time. But it tells that we cannot precisely determine that particle position nor the momentum at the same instant of time. By that we may guess that P and X in quantum mechanics wouldn't be directly useful or applicable or employed in quantum mechanics, rather than we are needing some we need some different terminology, which is wave function here can work perfectly to describe this nature of the particle, because now we are describing in the view of quantum mechanics, not classical mechanics. So this is the wave function psi describe the particle in same manner with the equation of motion, but in analogy figure, because it's due to its duality, it's not only particle. So this is like the cat head and its body is like the wave, because it's wave duality, it's moving together, and this is the quantum mechanics meaning. While in the classical mechanics it's only the head of the cat, which is the body, it's the material bulk and its particle itself. So if particle moving along with some suggested direction, maybe it's x direction or y or z, so it would be only one direction movement. So at any position and momentum of time, then this particle behavior can be described and shown through psi which is function of two variables, x and t. So this is the wave function. It's time dependent now. It depends on time and the position. So this could be the wave function. This wave function could be applied into all mathematical application, like the squaring or integrated. It's integratable, and itself is continuous function. So to reach the answer, but how this calculation of integration and square to find the finite answer has been approached before. For time independent Schrodinger equation as resulted below. In the previous class we have shown how Schrodinger equation were invented to introduce the time independent Schrodinger equation, which is the this form that we have described before, but just we have rearranged into different form. So this is the time independent Schrodinger equation. If we are including the time, it will be time dependent Schrodinger equation, and we are introducing here some different values like I, and this is blank h prime, which is blank constant, divided by 2 pi, which is 1.06 10 to minus 34 joule per second, and this is the derivative of wave function with respect to the time, and this is the potential energy of that moving electron to the 1d x direction. This is again the wave function, and this is a square root of the h prime divided by the mass, which would be electron or any particle, and this is the second derivatives, which is I think this is x and t. This is because this is some wrong happened here, that we need to add t here, divided by square root of x. So this is the second derivative with respect to the position. So I actually it's imaginary number, so it's square root of -1. And how could we are applying some imaginary number to be applied into the Schrodinger equation, which Schrodinger equation is still describing some real values, real particle. So how can we applying such value into this equation, and what is the meaning of this value? Actually, it's maybe if we are simply describing this value, it could be as symbolizing the idea of a quantum mechanics complexity. So this is to tell how it's complex is a quantum mechanics or Schrodinger equation describing the particle. Complexity comes from the duality nature of the particle movement. So to tell how it's complex, we are describing it through the imaginary number, which is I. So this is one-dimensional Schrodinger equations, either it's dependent or time independent. It's actually not derived, rather it's invented. It was checked through experimental, and it was also approved through many rechecking and experimentally until we have approved or Schrodinger approved the validity of this equation. There is no way to derive it numerically or mathematically. It's the same way with quantum classical mechanics, Newton's law, who has invented the second law of motion experimentally. So how this equation work? If we can see the shape, if we have reached to know the shape of wave function, which is depends on two variables, x position and time, at any specific timing, we can predict the future and expect the motion of this particle, as we already knew the shape and behavior of this wave function. So how could we get time independent from general time dependent? So this is the equation that we have shown before, how we have reached to this equation. So this is time dependent. So how can we get, and sorry, this is xt. So how can we get time independent from time dependent? It's simply, in mathematics, if there is function which is function of two variables, we can rewrite this function into two separated functions. This is not the same value of this. This is could be lowercase or any variable name, but we are just to keep the form of some well-known Schrodinger equation forms. We are keeping this simple, and this is different than this value. This is, suppose it's higher case and this is lower case, and g of t could be any function. So substitute this value into this equation, we can get this rearranged Schrodinger equation, time-dependent Schrodinger equation. And by dividing this value by the lower case of x and g of t, this is the two subdivided mathematical functions, we will get this equation. That means the right hand side equal the left hand side, and both of these values will reach into constant value. So we could rename this side into some constant value. E, it's not energy here, but it's any constant value. This could be any simple, I mean this is E. We will get this simple equation, and if we again multiply this whole equation by psi, this is lowercase psi, which is the part of the wave function, we will finally reach to the time-independent Schrodinger equation. So this is how can we tell and derive time-dependent to time-independent Schrodinger equation. They are related to each other. So we have in this class described the duality nature, what is the wave function, what is time-independent and time-dependent Schrodinger equation, what is the classical and quantum mechanics view of describing the system or any particle moving into any direction. So this is today's class.